Morning, everyone.
She's looking pretty fine to me now. Hush, baby, 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 baby. No, 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 you gonna go, I'm gonna slide your ways. Gonna take to the sky. Honey, nothing's gonna harm you, baby. I said, honey, nothing's ever gonna let you down. Oh, I just wanna do it. Hush, baby, 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 baby. No, 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 no.
All right, how are we doing this morning? I forgot to release the partial differential web work. Remind me if I don't do that right after class. Send me an email. How much time should you spend reviewing linear algebra? I mean, you might expect one question on the midterm since, you know, we don't have that much material. So yeah, you might expect a question on the midterm. We did skip a chapter. So I mean, I'm going to believe that it's chapter 13. We will come back to it later on. Questions in the meantime? Everybody's doing all right with the material? Yeah, the midterm is 3 hours, so 6.5 hours. How many questions should you expect for the exam? I still have not written it, but something like 4 or 5 questions. I mean, we don't want it to be too long. So, I mean, it's 3 hours, but I mean, there's no reason that it should take you 3 hours. There'll be no epsilon delta on the midterm. I understand it's difficult. I wanted you to tackle it, but it will not come up. All right, let's move on. Let's move on by going back to the partial derivative and how we defined it, right? The idea was this. You have this function z equals f of xy, and if you fix a point AB and look at its image, we said that we can fix B and just look at how x varies. This is going to define a curve, right? So if you were to cut this in the direction of x, this just defines a curve in the y equals b plane, right? So you're cutting it like this. And we asked the question, are methods of rationalization valid for limits in higher dimensions? I mean, there is one question that can be kind of done with rationalization with the understanding that continuity plays a role, right? So you can get some limits by a different argument, different from the epsilon delta, right? By making use of continuity. So short answer, yes. You have to justify a few things, but it works. Right, so we saw that if you cut, you get a curve. And we asked the question, what is the tangent line to that curve? And you saw that the partial derivative of f with respect to x gives you the slope of the tangent line, right? So fx of AB is slope of the tangent line. So the tangent line is going to be z is the derivative at AB times x plus something. Let's not worry about what that something is. It doesn't matter. In the plane y equals b, or if you want a parametric representation, let's take x to be t, y is going to be b, and z is going to be f of x at AB times t plus some b1. b1 which we don't know. Well, I mean, we can work it out, but I mean, we don't really care here. Similarly, right, if you cut it the other way, if you cut it on the plane x equals a, fy is going to be the slope of the tangent line. So the tangent line in the plane x equals a is Fy of AB times y plus something, whatever that something is. Or again, a parametric solution or a parametric form, y equals t and z is Fy of ABT plus some B2. Where am I going with this? We're going to ask the question, what plane has both of these tangent lines on them? So what plane has both lines on it? And we call this the tangent plane. So in higher dimensions, or I mean in 3D here, we're not interested in a tangent line, but rather tangent plane. Hello, Taha, nice of you to join us. So tangent plane is what we're interested in. Namely, the plane which admits both of these lines. What about 4D? It's a valid question. I guess you would have some sort of 3D space, right? Because in 2D you have a line which is the equivalent of an axis. Here you have a plane which is equivalent to the xy plane. And in 3D space, I guess you would, in 4D, I guess you would have a 3D XYZ space equivalent. So the question is, what plane admits both of these lines? And these lines have direction vectors. So the direction vector to the first tangent line is what? It's 1, 0, fx. The direction vector to the second line is 0, 1, fy. So the normal to this plane is going to be the cross product. And what is it? Negative fx, negative fy, and 1. How we found the vector coordinates? Well, we have the parametric equation of the tangent line here. So it's whatever has a t in front of it. 1, there's no t's here, so 0, 1, 0, fx. 0, 1, fy. So your tangent plane, cross product, yes, certainly. Right? D1 cross D2. Cross, cross, cross. We're looking for a vector that is perpendicular. Right? The tangent plane should admit both of these lines. So both of these vectors need to be on the tangent plane. No, it is fx of AB. I was just lazy. This is fx of AB and fy of AB. Absolutely. So there's your normal, and consequently the tangent line. So the tangent plane has the form minus fx of AB times x plus or minus fy of AB times y plus z equal to something. There it is. This is the equation of the tangent plane. How are we doing? Let's do a few examples from the book. Everybody with us? The question is asking us to find the equation of the tangent plane at the given point. So the tangent plane is the span of the two tangent lines, depending on fx and fy, exactly that. So to get the direction vector, we replace every constant by 0. No, this is linear algebra business, right? The equation of a plane is some point plus t times the direction vector. So the direction vector is the coefficients of t here, 4, minus 1, 1. This is why we reviewed linear algebra, right? So there would not be this confusion. Grisha is asking, what is D? The book makes it slightly clearer and tells you exactly what is D, but my point is, I don't care too much about D. You figure out what it is by taking a point on the plane and making sure that it satisfies the equation. Let's illustrate with this example. Right, you have z as a function of x and y. First of all, should we check that this point is on the surface. It's always a good idea, right? 4 squared is 16. This is 2 squared, which is 4. Times 2 is 8. 16 minus 8 is 8. Minus 5 is 3. So this point is on the surface. Let us work out fx and fy, or dz dx and dz dy. dz dx, 2 times x plus 2. So dz dx at the point and I don't know if you had seen this notation before, but if you had not, please take note of it. This is the derivative evaluated at the point. So at the point 2, 3, 3, this is 4, 8. dz dy, again, we differentiate with respect to y, treating all the other variables as constants. Minus 4x y minus 1, rather. And dz dy at the point 2, 3, 3 is minus 8. And consequently, the normal to the tangent plane, which is negative fx, negative fy, 1, fx we just found to be 8, so that is negative 8. This is positive 8, and 1, this is the normal to the tangent plane. And so your tangent plane has equation minus 8x plus 8y plus z is equal to something. Some d, we don't know. Z is equal to something. Some d, we don't know what d is, but we do know that this point must lie on the tangent plane, right? We're looking at the tangent plane at that point. So minus 16 plus 24 plus 3 is equal to d, and that is 8, 9, 10, 11. So d is 11. In other words, your tangent plane minus 8x plus 8y plus z is equal to 11. How are we doing here? Right, geometrically what's happening, it's the equivalent of the tangent line, right? I mean, you have your function here, and at some point, instead of just looking for a line, you're really looking for a plane which just touches the point. How do we know 2, 3, 3 is on the plane? It's given exactly. It's given. We're looking for the tangent plane at this point. Very much like you're given, I mean, think back to count 1, you're looking for a tangent line at some given point. The point has to be on the tangent line. Here, the point has to be on the tangent plane. Convinced? Questions? Shall we try a few more. Same question. We're looking for the tangent line to this function at the point 0, 3, 9. 0, 3, 9 easily seen to be on the function, right? When x is 0, this is 1. And when y is 3, the whole thing is 9. 9 times 1 is 9. Looking good. Take the partial derivative of z with respect to x. What is it? Easily seen to be this. So dz dx at the point is 9. What about dz dy? E to the x is treated as constant. Derivative of y squared is 2y. And so the derivative at the point when x is 0, y is 3, the whole thing is 6. And consequently, your tangent plane has the form minus 9x minus 6y plus z is equal to d. And if x is 0, y is 3, z is 9. So that is minus 9. In other words, 9x plus 6y minus z is equal to 9 is the equation of your tangent plane. How are we doing here? Somebody want to answer Edwin's question? How did these 6 and 9 become positive? Why do we need to write the whole coordinate point at the bottom when we only want the value of y? Right? I mean, you don't only want the value of y because this is a function of both x and y. Thank you, Edwin. And the reason I do that is because the book does that as well. And so you don't want to be caught by that, right? I mean, according to this, the whole tangent plane would have been minus 9x minus 6y plus z is equal to minus 9. And if you multiply the whole thing by minus 1, you get that. Sometimes the book multiplies by minus 1. Sometimes the book multiplies by other constants to maybe get rid of fractions, or if there's a common multiple throughout the whole equation, that kind of thing. So we'll be on the lookout for that. Do we want to do one more? Questions? Again, let's just make sure that this point is on the surface. Negative 4 over 4 is negative 1. Looking good. Let's consider dz dx, which is 1 over y squared. So dz dx at the point is what? 1 over 4? dz dy is easily seen to be minus 2x over y cubed. So dz dy at that point 8 over 8, which is 1, is that correct? Isn't the midterm usually 1.5 hours? In a regular in-person exam, you might expect 2 hours. You might expect 2 hours. Here I'm giving you 3, and then the school is giving you another 3.5. Look, I mean, there's no reason for you to spend 6.5 hours on the midterm. I mean, of course, you are allowed to spend that much time, and that's really up to you, but it should not take you that long. Of course, you want to be perfect, and you want to get 100 on the midterm, so maybe you're going to spend 6.5 hours, but if this had been an in-person exam, 2 hours would have been sufficient. Let's put everything together. The tangent line, or rather tangent plane, therefore has equation minus 1/4 x minus y plus z is equal to d. And when x is at the point, we get a 1 minus 2 minus 1. That is minus 2. In other words, minus 1/4 x minus y plus z is equal to minus 2. Or once again, I think it's going to be doable in 2 hours. It's all possible to get 100 in 3 hours? Yes, it is. Yeah, it is possible. I mean, most people don't get 100 in an in-person exam, but a lot, I mean, some do. I'm just saying most do not, because most make a few errors along the way because they're pressed for time and what have you. But if you have 6.5 hours, or if you have 72 hours, then you can spend as much time as you want and make sure that you don't make those silly mistakes. So the proportion of people who get 100 on online exams is much higher than on in-person exams. It's tangent plane, right? Don't make that mistake. Don't make the mistake I made. I called it tangent line originally, but it's tangent plane. And why are we adding negatives? I mean, it's not just here, right? It's everywhere. Everywhere we added negatives. And that's because we saw that the normal was given to us by this. Right, this is the first thing we worked out this morning. The normal to the tangent plane, the plane that admits both tangent lines, if you will, had this as a normal. Questions? Let's go back to Cal 1, where if y is equal to fx at the point AB, well, let's say this. If y is equal to fx, the tangent line at x equals a was given by, I mean, you know the slope is the derivative, right? So you take the derivative and that gives you the slope of the tangent line. And then you get some value b where if x is a, y is f of a. So this is what? When x is a, y should be f of a. So b is f of a minus f prime of a times a. In other words, the tangent line is f prime of a x plus f of a minus f prime of a times a. If we wrote, right, I mean, that's what I was going to do here. I was going to point out that the book would probably give this tangent line as x plus 4y minus 4z is equal to 8, and that is absolutely fine. Right, what have we done here? We have worked out the tangent line. Right, this is the tangent line. This is the tangent line from Calculus 1 that you're very familiar with. Let me rewrite this by bringing the f of a to the front and factoring out an f prime of a from the other two terms, leaving you with an x minus a. Right, so this is a reworked tangent line, right? It's the equation of the tangent line, just rewritten differently. And now, I mean, you have some additional knowledge, right? And you recognize that the tangent line is really exactly, it's the first two terms of the Taylor series expansion. It's really the first two terms of the Taylor series. Geometrically, what's happening, if you have a function, we're saying that for values close to a, the tangent line is a good approximation to the function. So for values close to A, the tangent line is a good approximation. To the function. And the same thing generalizes to higher dimensions. At a point AB, the tangent plane is a good approximation to the function. So the tangent plane so again, what is the equation of the tangent plane, right? So I mean, if you have z equals f of xy, the tangent plane has at the point AB is what? It's minus fx at the point AB times x minus fy at the point AB times y plus z is equal to something. Let's work out what that something is. Let's work out what that something is, right? Because you know that if x is A and y is B, then z is f of AB, so i.e. the point AB f of AB is on the tangent plane. So minus fx of AB times A minus fy of AB times B plus f of AB must be equal to D. So that's what D really is. And so your tangent plane right? Your tangent plane, if you solve for z, z is, bring the fx to the other side, so it becomes positive. Fy of AB y plus d, which is this business. And if you bring this to the front, f of AB, and if you combine these two, factoring out an fx, x minus a, and if you factor out an fy, y minus b, and there you have it. This is the equation of the tangent line, tangent plane, and this is going to be an approximation to the function for values close to AB. So this tangent line approximation here, also known as, this was known as tangent line approximation. Or linearization, if you remember linearization, if you remember from Calculus 1, this is now known as tangent plane approximation. or linearization once again. And it brings up the question that we had that came up naturally a while back. If these are the first two terms of a Taylor series, are these the first three terms of Taylor series in higher dimension? And the answer is yes. Exactly that. Convinced? Shall we consider an example? The question is asking us to find the linearization of the function at the given point. Well, that's suspense. It's because I was trying to come up with the phrase ancient astronaut theorists say yes, but it wasn't coming out, so I ruined it. All right, so we're going to linearize the function. Right, we're going to get an approximation to the function using the tangent line. So let's work out the partial derivative. Partial derivative with respect to x is derivative of sinus cos times the derivative of the inside with respect to x, right? Has everybody mastered partial differentiation? I mean, we didn't discuss it at the beginning of today's class, but I mean, I suspect there are no issues, right? I mean, it's very easy. You've mastered the regular derivative. Now you just treat all the other variables as constant. So we're differentiating with respect to x. Y is treated as a constant. You're good to go, right? Everybody? We're good with that? And the derivative at 0, 3, if x is 0, cosine of 0 is 1, y is 3, this is 1/3. Similarly, let's differentiate with respect to y. You've got a sum here, 1 plus derivative of sinus, once again cos, times the derivative of the inside with respect to y this time, right? So minus x over y squared. 0.03. When x is 0, cosine of 0 is 1. This is 0, so everything disappears, and we're left with 1. So linearization, right, or z, which was really your function for values of xy close to 0, 3. What is your function at 0, 3? Sine of 0 is 0. So this is 3. Derivative times x minus 0. Derivative with respect to y times y minus 3. Let me put a 1 here for completeness. There it is. So this is the linearization of your function for values very close to x equals 0 and y equals 3. So very close to the point 0, 3. Your function is going to be approximately this. Questions? Right, a tangent plane approximation, also known as linearization. An immediate generalization as to what was happening. Isn't it minus 1/3? Is it minus 1/3? I mean, there's no minus, right? Because I've brought everything to the other side. Why is it 3? Here, your function at 0, 3, have I made a mistake? When x is 0 and y is 3, when x is 0, this whole thing is 0. Sine of 0 is 0, and y is 3. So the function is 3. 3 and minus 3 cancel. They do. So this is really 1/3 x plus y. Absolutely. What's the difference between this and what we were doing before, namely finding the tangent plane? There's really no difference, right? It's just a different way of looking at it. It's just a different way of looking at it. This is really your tangent plane, and we're saying that the function is approximated by the tangent plane near the point 0, 3. So would the approximation for the tangent plane and the approximation, so would the equation for the tangent plane and the approximation be the same? In fact, they are, right? This, we just saw that this is the tangent plane. This is the tangent plane. Z equals that. And the linearization is just this right-hand side. Right? Your function, because this is the tangent plane. This is the tangent plane for z equals f of xy at the point AB. This whole equation here. Whereas the linearization is just the right-hand side. So your function z was equal to this at the point AB, and now for values close to it, everything is approximated by the right-hand side. Compare with the calculus 1 equivalent, right? Tangent line versus linearization. Some books will define the linearization LXY as this right-hand side. So if you want, let's define LXY, the linearization of your function, to be this. Versus the tangent line, which is z equals that. Versus, again, I said tangent line, but I meant tangent plane, which is z equals. Which is this. But when we do a Taylor series with power 2, is it still a linearization? Not anymore, right? It's more linear than the original function. Let's not say more linear. The problem with the power 2 is x squared is not a linear function anymore. So that's why the term linearization would not be appropriate in that case. What it is, though, is a better approximation. So no longer linear, no longer a linearization, but rather a better approximation. Questions? Moving on. Let's move on to the chain rule. And let's recall the chain rule from calculus 1. Let's recall that the derivative of y with respect to u, or with respect to x, is dy du dx. Right? This is the chain rule you know and love from Cal 1. What we want to do I don't know what black pen, red pen actually is. But so this is the chain rule from Cal 1. And let's generalize this idea. Suppose, right? I mean, and you know, I mean, this was in the case that y is a function of u, and u is some other function of x. So when you compose the two, that's what's happening. So in that case, we have the chain rule from Cal 1. Let's generalize this idea. Suppose you have a function of two variables where x is a function of t and y is also a function of t. You see what's happening? In that case, if you were to plug those functions of t in, z would be just a function of one variable, a function of t. So it would make a lot of sense to ask, what is dz dt? Notice it's not the squiggly d's now, it's the regular derivative, because your function is really just a function of one variable, t. And if you were to plug those in, you would get a function of t for the x and a function of t for the y. How do we differentiate? Well, you can differentiate df dx. Differentiate with respect to the first variable times the derivative of the first variable with respect to t plus df dy dt. Let's illustrate. Let's illustrate with an example. The first two are partials, and the second two are regular. Let's take an example to clear this whole thing up. Consider the function e to the xy sine y, where x is t squared and y is t cubed. Right? So in this case, if you substitute, let's just substitute in, see what happens. This is e to the t squared times y, t cubed, sine of t cubed. Convinced? All right. And now, if you were to differentiate this, well, you would have no issue differentiating that, right? First of all, this is a function that depends only on one variable, t. So you're going to differentiate the regular derivative way, right? dz dt. Why did we choose these values of t for x and y? This is just an example. Just a particular example to illustrate what's happening. Right? How would you differentiate this? It's just a function of t, so you're differentiating the regular way. And you've got a product here. So product rule applies. No, it's not that we're choosing random values. This is just an example. Just an example. I mean, in general, you have absolutely no freedom whatsoever. The question gives you the functions. So I'm illustrating the chain rule. If you differentiate this, how do you differentiate? As a product. So product rule applies. Let's differentiate the first one. Derivative of e to the something is e to the something times the derivative of the inside, and the inside is a product. I mean, I could have simplified, but let's not do it. Let's leave it as a product. So you're going to apply the product rule, differentiate the first one, leaving the second one fixed, plus leave the first one fixed, differentiate the second one, leaving this fixed, plus leave the first one fixed, differentiate the second one. Derivative of sine is cos times the derivative of the inside. Now, let's look at the parallel between the ZDT that you found, the regular way, versus what the chain rule suggests. In other words, let's work, right? So this is the left-hand side. Let's do it using the right-hand side. What is, going back to this, what is df dx? Well, the only thing that depends on x is this. So it's e to the xy times the derivative of the inside, which is just y, leaving the sine y fixed. Similarly, df dy, now you've got a product, so product rule applies. E to the xy times the derivative of the inside with respect to y, which is x, leaving the second one fixed, plus leave the first one fixed, differentiate the second one, derivative of sine is cos. dx dt is easily seen to be 2t, and dy dt is just 3t squared. So if we put everything together here, df dx is this, times dx dt plus df dy is this, times dy dt, which is 3t squared. And if you replace everything, if you replace x with t squared and y with t cubed, so x is t squared, y is t cubed, e to the t squared times t cubed, y is t cubed, sine of t cubed times 2t, plus this whole thing times 3t squared. Do the answers correspond? Can you please repeat this differentiation? Well, let's just go with it for now. Let's make sure that the answers coincide. We did it one way, the regular way here, and here I applied this chain rule formula to get this. Do the answers agree? Here I have, let's look at the cosine one. This times 3t squared, exponential cosine 3t squared. So these certainly agree. And then let's look at this first one here, the exponential times t cubed times 2t times sine t cubed. So this and that work out. And the exponential, t squared, the sine, and the 3t squared again. Oh, wait. Yeah. Yeah, there it is. Yeah, the functions x and y have to be given. The function, right, again, yes. Let's just say yes. So what I'm saying here with this version of the chain rule, we're saying that if x and y are functions of t, then z is a function of t, and to differentiate, I'm not sure why everybody's caught up on the fact that I'm using t squared and t cubed. This is only an example. Only an example. All I'm saying is that in order to differentiate z with respect to t, you have to hit everything that contains a t. Short answer, yes. Do answers always have to be in t and not x and y? Sure. But this is just one version of the chain rule. We can generalize. What if you had z as a function of x and y, where x is a function of s and t, and y is a function of s and t? Then we can ask the question, what is the derivative of z with respect to s? What is the derivative of z with respect to s? What is the derivative of z with respect to t? Right, because x is a function of s and t, y is a function of s and t. So if you plug those in, z would be a function of s and t. And what's the derivative? Well, to differentiate z with respect to s, and both x and y have s's in them. So dz ds is dz dx, dx ds, plus dz dy, dy ds. Similarly, dz dt is dz dx, dx dt. plus dz dy, dy dt. Right? You gotta hit everything that has a t. And you can go on. We're gonna stop here, but there are infinitely many chain rule variations. We cannot write all of them down, but you can make up your own. The book likes to suggest a tree diagram to illustrate what's happening, right? You have z as a function of both x and y. And x and y are themselves functions of s and t. So to differentiate z with respect to s, you need to go through these two branches. To differentiate z with respect to t, you need to go through these two branches. And so on and so on. Let's take a few examples from the book. Now, I feel I must stress that this is a particular example from the book, right? What if y was only a function of t? An excellent question. But x was a function of s and t. So you're really suggesting that you're going to make up a different chain rule. So if y is only a function of t, let's make up an appropriate chain rule. If you want to differentiate z with respect to s, dz ds, well, there's only an s right here. So dz ds is dz dx, dx ds. Right? X is still a function of two variables, so partial derivative here. But dz dt, there's a t here and a t there. So dz dx dx dt plus dz dy dy dt. And now notice this is a regular d because y only depends on the single variable t. Partial and regular derivative certainly matter in theory. In practice, you know they really don't, but there it is. So you see yet another variation of the chain rule. Very nice. Let's do this two ways. We're looking for dz dt. So the regular way, by plugging everything in, z is really t squared times 5t e to the 5t. Or if you prefer, 5t cubed e to the 5t. So dz dt, this is easy to do, right? This is just a product. So product rule applies. 15 t squared e to the 5t plus 25 t cubed e to the 5t. The regular derivative that you're used to working with. We're good to go. What about the other way? What about using the chain? What does the chain rule say? Well, so z is a function of x and y, and both x and y depend on t. So dz dt is dz dx, dx dt, regular derivative, because x only depends on one variable t, and dz dy, dy dt. So, what is dz dx? Differentiate with respect to x. What do we have? Y e to the y. I think we can read that off, right? Times dx dt, which is 2t, plus dz dy, the derivative of this with respect to y. Let's leave the x out because it's a constant, and we're differentiating y e to the y, which is just a product, so product rule applies. Differentiate the first one, leaving the second one fixed, plus leave the first one fixed, differentiate the second one, times dy dt, which is easily seen to be 5. Let's replace the x's and y's with their t counterparts. And this is 5t e to the 5t, and t squared e to the 5t plus 5t e to the 5t times 5. Do these things agree? I don't know that they do. This is 10t squared e to the 5t plus another t squared e to the 5t, so that should be 11. What is that? Oh, I've got a 5 here. So 10 plus 5 is 15 t squared e to the 5t, so that's good. And the rest is 25 t cubed e to the 5t, 25 t cubed e to the 5t. Beautiful. How are we doing? Is everybody with us? Questions? So the most convenient way to determine the derivative, either normal where chain rule will be the situation, will be situation dependent. I think so, yeah. It's important for you to be able to do both. The point is that the most interesting questions don't give you the possibility of doing it the first way. Don't give you the possibility of doing it the normal way. But here we have the possibility. So let's do it, you know, for fun. Let's do two questions. One of them will do one way, the other will do the other, and that'll be sufficient. So let's do this the normal way if you want, right? Where z is really e to the pi t minus e to the minus pi t over e to the pi t plus 2 e to the minus pi t. So dz dt is what? I mean, what do we want to do here? Do we want to simplify that? Maybe multiply by 1 e to the pi t over e to the pi t. You know, you can do whatever you want. I think it might be easier to work with this so that dz dt is simple. Well, in fact, do I want to add 2 and subtract the 2? We're just looking for the simplest way to do this. This is going to be 1 minus 3 over e to the 2 pi t plus 2. So now it's trivial. The derivative is easily seen to be 3 6 pi e to the 2 pi t over right, a little bit of manipulation goes a long way here. I'll let you do it the other way and convince yourselves that the answers coincide. Same question, different function. And here we'll do it the chain rule way, right? Where you understand that all three functions, x, y, and z, but all depend on t. If you wanted to draw a tree diagram, if you will, both z depends on x, y, and z, And that is not good form here. It must have been a W. Must have been a W. So W depends on X, Y, and Z, and all three of X, Y, and Z depend on T. So you see, to differentiate with respect to T, you got to go through all three branches. Let's take a moment to simplify this as 1/2 ln of x squared plus y squared plus z squared. Much better. And let's write down the version of the chain rule that is important to us here. dw dt, because w really is just a function of one variable t. So it's the regular derivative. dw dt is dw dx, dx dt, plus dw dy, dy dt, plus dw dz, dz dt. So dw dx, what is the derivative of this with respect to x? I think it's easily seen to be x over x squared plus y squared plus z squared times dx dt, derivative of x is derivative of sinus cos. dw dy, well, similarly, I mean, you see that there's symmetry. If you interchange the x's and the y's, the function stays the same. So the derivative should be the derivative, but the x's and y's interchange. So y over x squared plus y squared plus z squared. A nice little argument we made yesterday. Times dy dt, so times negative sign. And similarly, the derivative with respect to z, well, if you interchange x and z, it's still the same function. So the derivative should be just the x's and the z's interchanged. And dz dt, derivative of tangent, is secant squared. Plug in the t values. Where is the 1/2? Exactly. Somebody want to address that? Where did the 1/2 go? Exactly. It comes from the square root, but the derivative of x squared is 2x, so the 2's cancel out. There it is. Sine cos minus sine cos. And z is tangent times secant squared over sine squared plus cosine squared, which is 1. 1 plus tangent squared is secant squared. Blah, 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 the whole thing is tangent. Did I lose you, Grishko? Where did I lose you? Are we good? I mean, this could have been forecasted, right? I mean, if you just plugged in sine squared plus cosine squared is 1, 1 plus tangent squared is secant squared, square root of which is secant. So we're really just differentiating ln of secant. So the derivative is z. Interesting. Yeah, interesting. All right, shall we try one with how does the bottom add to secant squared? X squared plus y squared is sine squared plus cosine squared, so that's just 1. Z is tangent, so the denominator is 1 plus tangent squared, which is secant squared. All right, so let's do this 2 separate ways, just to as a one last chain rule example. Right, you understand that x is rather z is a function of x and y, and both x and y are themselves functions of s and t. Right, so again, a tree diagram, if you will. Z depends on x and y both depend on s and t. So z really depends on s and t, and we can ask the question, what is dz ds? What is dz dt? Would we have lost points if we have left it as sine squared plus cosine squared plus tangent squared? It's not as simple as I would have wanted it to be. This is the answer I would be looking for. Very nice, concise answer. So that's what you should be striving for. Right, so the chain rule tells us dz ds is dz dx, dx ds, plus dz dy, dy ds. Similarly, dz dx, dx dt, plus dz dy, dy dt. It's neither of those. It's neither of those. It's an s ln t. S ln t. Oh, it's actually the second one. Yes. And this is t e to the s. Right, so Chain rule. Let's just do one. Let's do one of them, but we'll do it in two different ways. Right? So Z, if you just plug in, Z is really arctan of S squared ln squared of T plus T squared e to the 2s. So we can differentiate with respect to S and with respect to T. So dz ds, what is that? Well, the derivative of Z, derivative of arctan, is 1 over that business, or 1 plus that thing, one over 1 plus u squared is dx by dx equal to 1? Yes, indeed. Indeed it is. So this times the derivative of the inside with respect to s. So that is 2s plus t squared e to the 2s times 2. Right, very easy if you can plug in. There's really no ambiguity there. Now let's make use of the chain rule. This part is what? dz dx. So that's 1 over 1 plus x squared plus y squared all squared times the derivative of the inside with respect to x. And dx ds is just ln t. dz dy, same thing. 1 over 1 plus x squared plus y squared all squared times 2y, right? Derivative of the inside. And then dy ds is t e to the s. Let's not plug in. Maybe it's going to be easier to see here. First of all, observe that your denominator is exactly 1 plus x squared plus y squared all squared, right? Because this is, because x, so this is x squared, and this is y squared, right? And your numerator, if x is s ln t, this is 2s ln of t squared. 2s ln of t squared, it's right here. And then the second one, y is t e to the s. So you get 2 t's and 2 e to the s's. So 2t squared e to the 2s. 2t squared e to the 2s. It's beautiful how everything works out. And when you're differentiating, you have to ask yourself, what am I doing? The derivative of arctan is 1 over this squared, so that's fine. But then when you differentiate the inside, here you're differentiating the x squared, which is going to be 2x times the derivative of x with respect to s. It's all there. You get overwhelmed just looking at this formula. But when you're doing it, you're actually doing this formula without realizing it. That's what's happening. let me point out, while I have this chain rule version up here, that you can rewrite this business as a matrix equation, and a very important one at that. Observe that dz ds, dz dt can be rewritten as dz dx, dz dy times dx ds, dx dt, dy ds, dy dt. Is that true? Is that true? If you multiply this and that, dz dx, dx dx, dx ds plus dz dy, dy ds, and that's exactly that, and same for the other one as well. What was the question asking for? dz ds or dz dt? It was asking for both. We only did one. I'll let you do the other one. And it's squiggly D, right? But yes, it was asking for both. We only did one because, I mean, these are time consuming and we don't want to waste too much time. So the other one is left as an exercise. Yes, exactly that. Right, so my observation to you is that the chain rule can be written this way. Right, these two. So in other words, this version of the chain rule can be written as this nice matrix equation. And we haven't seen yet, but I claim that this is an important matrix known as the Jacobian. We will encounter the Jacobian over and over. So it is matrix multiplication, absolutely. And these things are actually Jacobians. They're all Jacobians. We'll encounter this matrix momentarily, a little later on today, time permitting. Let me take this time to introduce some notation here. This Jacobian, so this matrix, the matrix dx ds, dx dt, dy ds, dy dt, known as the Jacobian, has a nice, well, I mean, it's just this. This matrix is the Jacobian, and it's usually denoted dxy by dst. So it's just a name for that matrix. We'll see that it has special properties. But right now, this is notation for the Jacobian, which really just means this matrix. So the left one is a Jacobian of z exactly, right? This could be thought of as dz dst. Absolutely, right? You've only got the one function, so dz by dst, and this is dz dxy. And so the chain rule has this nice reinterpretation in terms of Jacobians. dz dst is equal to dz dxy times this big one, which is dxy by dst. And in a terrible abuse of notation, you can think of canceling these out, and you get dz over dst, exactly what you started out with. In exactly the same way that it's terrible abuse of notation, df dx is df du, du dx, right? The chain rule in the one variable case where you think of canceling out these du's, which of course you are not allowed to do, but you can do it in your head, and you get df dx. If you only had one function and one variable, then exactly dx ds. Yeah, terrible abuse of notation, but we use it anyways because it works. It works. You're not allowed to cancel these, but even if you did, yeah. So all I'm saying is the chain rule has this nice reformulation in terms of Jacobians, and everything works as it should. Let's go back to this. And the question is asking us to find dy dx. What is that? What's happening here? This is really an implicit function question, right? I mean, it's asking for dy dx, the regular derivative of y with respect to x. You have y implicitly defined here, exactly that implicit differentiation, thank you, Benjamin, from Cal 1. So you can assume y is a function of x and differentiate the whole equation with respect to x. So what do we get? Derivative of cosine negative sine times the derivative of the inside, but inside is a product, so product rule applies. Differentiate the first one, leaving the second one fixed, plus leave the first one fixed, differentiate the second one, and do the same on the left. Derivative of 1 is 0, derivative of sine is cos, times the derivative of the inside, dy dx. And you know what to do, right? Just multiply everything out, and we get minus y sine minus x sine times dy dx is cos. Bring the dy dx's to one side, factor and divide. Can we do that in our heads? it's easy to see that dy dx is equal to what? Minus y sine of xy divided by cos y plus x sine xy. Is that right? Are you doing that on paper? Does everybody have that? Thank you. Right, and you know, this is just Cal 1 techniques. Nothing fancy is happening here. My question to you is, can we generalize the idea? Right, I mean, let's look at this in a different light. We had cosine of xy is equal to this. Let's bring everything to one side. And if you wanted to generalize, how could we generalize this? Well, I mean, if you want to describe all the possible equations happening, what is this? This is some function of x and y equal to 0. Right? So all implicitly defined functions have this form. And we can ask the question, well, so first of all, theoretically, you might be able to solve for y as a function of x. But even if you cannot, in practice, theoretically you may, and the question arises, what is dy dx? What is dy dx? So we're going to do exactly the same thing. We're going to differentiate this equation with respect to x, assuming that y is a function of x. So you see, if you draw a picture of what's happening, f depends both on x and y is assumed to be a function of x. So f really just depends on x. And to differentiate with respect to x, well, you've got to do those two branches. So the derivative of f with respect to x, you want to differentiate the first variable, right? Because there's an x in there. And y, there's also x's in here because y is a function of x. So what's the derivative? What's the derivative of the left-hand side with respect to x? Well, we're going to differentiate f with respect to the first variable. Plus differentiate f with respect to the second variable times the derivative of the inside, right? Chain rule kicks in. Derivative of 0 is 0. So now it's easy to see that dy dx is minus f1 over f2. Let's see how this agrees. This was our function. If you differentiate this with respect to x, what do we get? We get minus sine of xy times y. Well, I mean, let's actually do it here. In our previous example, f was equal to cosine of xy minus 1 minus sine y. So f1 is big. Yes, f1 is notation for the derivative with respect to the first variable. So f1, the derivative with respect to x, is minus sine times the derivative of the inside. And f2, the derivative with respect to y, that's again minus sine times the derivative of the inside. And the derivative of minus sine here is minus cos. So minus f1 over f2, we have sine of xy times y over this, which is exactly what we had up here. So a very nice, concise way of expressing implicit differentiation. How are we doing? I don't have any squiggly dy dx anywhere. I still don't have squiggly dy dx's. I'm not sure what you're referring to. And is it the envelope theorem? I'm not familiar with that term. We call it the implicit function theorem. The implicit function theorem tells you you can solve this equation for y as a function of x, at least theoretically, as long as f2 is not equal to 0. You can apply the implicit function theorem if you want to work out the derivative. The derivative is dy dx is going to be this immediately. Is a notation for f1 and f2. Isn't f1 and f2 notation for the derivative? Yes. f1 is the derivative of f with respect to the first variable. f2 is the derivative of f with respect to the second variable. So the implicit function theorem tells you you can solve for y as a function of x anywhere near the point where f2 of that point is not 0. Anon, I'm not sure what question you're asking, unfortunately. Exactly, so we basically just solved for dy dx in two ways. First, using implicit differentiation, and second, using partial differentiation and getting this nice result. So in other words, proving the implicit function theorem. Exactly that. So now you have two options. And it's nice to convince yourself that the bottom is just the derivative with respect to the variable you want to solve for. And the top is just negative df1. Negative of f1 here. And this idea can be extended. Can be generalized. Let's illustrate. Does this generalize in higher dimensions? In fact, it does. It does, Nicholas, and we'll consider that momentarily today, hopefully. We can't find dy dx in terms of x only in this case? Probably not. You can never, in implicit differentiation, the best you can hope for is a derivative involving x's and y's. We did this question originally, absolutely. And yeah, we did this exact question. So the book repeats it. I wasn't going to do all of it, but only use it to illustrate the generalization. Right here you have one equation, three unknowns. So the best you can do is hope to isolate for one variable in terms of the other two. And in this case, they're suggesting that perhaps you could solve for z as a function of x and y. And in doing so, the question arises naturally, can we find dz dx and dz dy? And like you said, Qian, we already did this question. So let's just, let's just do the dz dx just to illustrate again what we're going to do. And we're going to use this example to generalize. Let us assume that z can be solved for as a function of x and differentiate the whole equation with respect to x, assuming x and y are independent variables and z depends on x. And so the derivative 2x plus 2z dz dx minus 2 dz dx is equal to 0. And again, very easy to see that dz dx is minus 2x over 2z minus 2. And we get exactly the end. Well, let's leave it as that. No need to simplify. That's exactly the answer we had originally, and we're all good. But now, can we generalize? Can we describe in general terms what is really happening here? And once again, if you bring this 4 to the other side, we have this big function, f of x, y, z, a function of 3 variables, equal to 0. Exactly. Exactly. As Benjamin suggests, we can make a more general implicit function theorem using this. And, think about what we did here. Theoretically, we said we could solve for one of the variables in terms of the other two. So maybe z as a function of x and y, or x as a function of y and z, or y as a function of x and z. All possibilities are open to us. Why did we keep the z terms and not the y? Well, the options are open. Usually the question will tell you what they want. And here, they're asking you to find dz dx and dz dy, so it's understood that they wanted z as a function of x and y. They could have just as easily have asked for dx dy and dx dz, meaning assume x is a function of y and z. But let's stick with the assumption that you can solve for z as a function of x and y. And if you differentiate the whole equation with respect to x, with the understanding that x and y are independent variables, and z depends on x and y, right? So again, f depends on x, y, and z, and z depends on x and y. So the derivative, well, this depends on x, and so does this. So the derivative of big F is going to be f1 times the derivative of x with respect to x, and that's what somebody was suggesting, which is just 1. I didn't put it originally, but I'm putting it here for completeness, plus the derivative of big F with respect to the third variable times the derivative of the inside. So you see, dz dx is negative f1 over f3. And similarly, I'll let you work it out, but dz dy, I think it's easy to see, right? You get f2 plus f3 dz dy. So that's going to be negative f2 over f3. You see the denominator doesn't change. Where did the f2 go? There is no f2 because y does not depend on x. We're differentiating with respect to x, and x and y are independent variables. So dy dx is 0. Yesterday we did this with dz dx, the straight. Did we really have a y there as well? If we had a y, then it was a mistake. Edwin, can you confirm? If we had a y, it was a mistake. It should have been the squiggly. Should have been the partial derivative. Right? And implicit function theorem tells you that you can solve for z as a function of x and y as long as f3 is not 0. So that's a nice generalization of the implicit function theorem. But you can generalize. You can generalize further. Yeah, the tree. I mean, I was not a fan of the tree before. I don't know that I'm a fan still, but it's not bad. It's not bad, and I mean, it kind of goes back to trees and probability as well, which is a very useful tool, and it behaves in the same way. So I'm warming up to the tree. Let's generalize that implicit function theorem, where you have two equations, three unknowns. Let's think about what we could possibly do. In the first one, you might be able to isolate for one variable in terms of the other two, right? So maybe z as a function of x and y. So from the first one, you might be able to write z as a function of x and y. If you plug that into this one, now you just have x's and y's in the other one. So you might, right? So now you just have a big equation of x's and y's. You might be able to solve for y as a function of x in this one. And now plug that back into this one. So z, which was a function of x and y, but y is a function of x. So z is really now just a function of x. And we can ask the question, what are the derivatives of z with respect to x? And what is the derivative of y with respect to x? Assuming y and z are functions of x. Grisha, or did I lose you? Are the two functions there related? What I'm suggesting is, consider the scenario where you have two equations, several unknowns. Here I'm saying two equations, three unknowns. Would it be more? Right? So two equations, three unknowns. Maybe you solve for z as a function of x and y in the first one, which is what we were assuming over here. If you were to do that in practice, or at least theoretically, imagine that you have that result. Plug that into the second one. Now you have a big equation involving only two variables, x's and y's, right? Because the z has been replaced by x's and y's. So now you just have x's and y's. Maybe you're able to solve for y as a function of x. And then plug that back into your z to get z as just a function of x as well. So now, 2 equations, 3 unknowns, you're perhaps able to solve for 2 of the variables in terms of the third one. Y and Z in terms of X. And in doing so, we ask the question, what is dz dx? What is dz dy? And let's see how we can solve for that. Right? So it's understood now that we were able to solve, at least theoretically, for y and z in terms of x. And let's differentiate both equations with respect to x, assuming, but why there is no more z in the second one. There are no more z's because you solve for z as a function of x and y in the first one, and you substituted that back in to the second one. So the second equation now is only in terms of y and x. So y is not going to depend on z. So if you differentiate, assuming y and z are functions of x, what's the derivative? Derivative of x squared is 2x. Derivative of y squared, 2y dy dx. Derivative of z squared, 2z dz dx. Derivative of z. Derivative of 4 is 0. Derivative of 0 is 0. Same for the other one. Okay. Here you have a product, so product rule applies. Y plus x dy dx. Again, a product. dz dx. Leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. Derivative of z squared is 2z dz dx. Derivative of 7 is 0. Derivative of 0 is 0. All right. Let's rewrite these properly. The first one, minus 2y dy dx. Let's factor out a z, a dz dx. So 2z minus 2 dz dx. And let me bring this 2x to the other side. And similarly, the second one, x dy dx. Let's factor out a dz dx. So I have an e to the x minus 2z. And let me bring the rest to the other side. Minus y minus z e to the x. So take a step back. What do we have here? We have 2 equations, 2 unknowns, right? What are the unknowns? dz dx and dy dx. So this is what we want. So you can solve for this however you wish. Right? dy dx and dz dx is what we're looking for. We are, well, z as a function of x and y originally, but then since y is only a function of x, it turns out that z is only a function of x as well. You see what I'm saying? Suppose you figured out z was x plus y squared, and then you figured out that y was actually sine x somehow. then it turns out that z is actually x plus sine squared, just a function of x. Let's finish this up. Let's solve for dy dx and dz dx however you want. Now that you've solved for it however you want, let's solve for it a way you don't want to solve for it. Namely, using Cramer's rule. And what does Cramer's rule tell us? It tells us that dy dx is the determinant of this business divided by the determinant of the original Cramer's rule, you know Cramer's rule. Let's quickly define Cramer's rule. Ax plus by equals c, dx plus ey is equal to f. Cramer's rule says that x is the determinant of CF, right? First of all, the matrix corresponding to this linear system is the matrix A, B, D, E. And then, so that's going to be the denominator. And then the numerator is this column taking the place of the column corresponding to X in the original. And similarly, Y is the same thing. So you replace the column corresponding to Y with this business. And there it is. From linear algebra, exactly. Exactly from linear algebra. And again, what I want to bring your attention to is the fact that we have the same denominator. And on Monday, we're going to generalize this idea to higher dimensions. Something the book does not do, but we're smarter than the book. The book is weak here. The book is very weak with respect to the implicit function theorem. All right. Think about this. Think about it because it seems overwhelming, but if you do a few exercises, it's exactly what you expect. It's exactly the generalization you would expect. All right, think about that. We'll pick this up again when is the exam actually? It opens up Monday at midnight, so a minute past midnight, Monday morning. And it closes at 11:59 p.m. Monday night. So you have a 24-hour window to do the exam. Once you have accessed the exam, you have 6.5 hours to do the exam and upload your answers. Today's material is not on. You compute the determinants, thank you, Joe. Exactly that, right? I mean, I've left it as this, but I mean, we're not actually finished here. So today's material is not included, it ended yesterday. All right, thank you all for coming, folks. Good luck Monday on your exam, and I will see you Monday in class. We will, again, generalize this notion. It's on CrowdMark, absolutely. You will receive an email from CrowdMark. If you do not receive an email from CrowdMark, please email me. And I will see you guys on Monday. Have a good weekend. And I'll see you next week.